So we're gonna get this started. I actually have the honor of introducing Eric Sachs. We go by Sachs because there were too many Erics at the company, and as it turns out, it was just easier to call him Sachs than it was to try and figure out which Eric we were always referring to. Um, so if you'll indulge me in a slight anecdote, I actually owed Codebeam for knowing Sachs and having Sachs as a friend because we met almost exactly during the last Code Beam in San Francisco, right before lockdown. We started chatting at about a bunch of ways that we could possibly connect Erlang up to hardware and actually use Elixir on hardware. And we were so far into it that I almost missed my talk. So we were chatting and talking and talking. And ever since then, we were fortunate enough to actually become colleagues and work together. We were also unfortunate enough to become colleagues and work together right as the pandemic started. So Eric and other members of our team, some of who are actually in the chat room here already, helped us deploy and build software to help support COVID response. And this was at a time, if you remember, sort of COVID is very much now kind of a thing that we live with. But at the time, nobody really knew what it was, and nobody knew what we had to do. And so Eric and a large team of people were all supporting us in several states in the United States to deploy COVID deployment software. And I will tell you, we spent a lot of long hours trying to figure out the best way to try and build some of these systems under some incredibly trying circumstances. And all I can say is I've seldom worked with a finer engineer and a finer human than Eric, because even when we were 60, 70, 80 hours in for the week, he always managed to find one more hour that he could put in or one more way that he could try and solve a problem because he knew lives were on the line. So without further ado, I'm going to basically let Sachs take it over from here and tell you guys about how a whole team of us were able to build software based on Erlang, Beam, and Elixir that literally took to the front lines of the fight in COVID-19 in the United States. So Sachs, it's all you.
Cool. Thank you. Thank you very much, Randall, for that. Again, this talk is using Elixir to fight COVID-19. And just like a brief introduction about what this talk is. I'm going to go over some of the technical, like a technical overview of some of the Elixir Erlang tools that we used, my personal experience with those tools and tool chains, as well as other languages, and hopefully not too much hubris, but one person's hubris is another's memoir. So let this be a memoir. So quick timeline of the talk, generally March through July. The beginning part of it more around other tools and tool chains, ending with the solution that Randall was talking about that we did in Broadway. So the beginning of 2020 was actually really incredibly productive for me. I was free. I had just quit my job, and I was actually curious to get back to Ruby on Rails, which was what I had done before I was working in Elixir and Erlang, and sort of test my newfound biases. But I instead actually spent a lot of time just going deeper into Elixir and Phoenix. But there was this, weird thing that kept showing up in the news, and I realized, getting into February of 2020, I really needed a job, and quick. And I was fortunate to have met Randall at Codebeam, or actually I had met him probably the previous week when I was interviewing at Geometer, but to actually spend time talking with Randall, and actually joined Geometer, which is an experimental startup incubator. And the intention was going to be a co-located team or multiple teams co-located in San Francisco. And one of the differentiators was sort of one team working towards social good with the other teams supporting that through working towards eventual investment. But 7 days before I started, the Bay Area announced its shelter in place. And on my first day, we had an all hands meeting, with the new reality, incredible risk aversion in investment, but also, real needs. And Rob, the founder, declared that for the foreseeable future, like we would just be doing things for COVID relief. And it was pretty clear that there were some big problems, personal protective equipment. And turns out we were only a small number of degrees of separation from the California governor's office. And we had the opportunity to potentially build a solution to this. actually track the real needs of the hospitals, but also make that apparent to the people in the governor's office doing real-time decisions about where things were probably going to be start failing next. I think this would have been a really fantastic candidate for Phoenix, but I was the only person on the team with production Elixir experience, so we did it on Rails. And as most of you probably all know, it was chaos. Everything was chaos. But it turns out that like large companies like Microsoft and Salesforce were also building solutions to this. And so once it was apparent that states were going to jump on board with these larger solutions, we shut the project down because states didn't really need two solutions, and they really didn't need our solution. So going forward to April 2020, I found myself in meetings with public health officials, people from philanthropic organizations to help make contact tracing work for the state of New York. They had already chosen a contact tracing vendor, ComCare, which is a generic platform for like custom workflows, i.e. forms that can be programmed via DSL, so kind of like a Drupal or WordPress, but for public health, but an inability to rapidly add integrations. And they had some key problems, like making phone calls. The most that they could actually commit to was things they could do with their DSL, i.e. like embedded links with a target equals blank in a browser. But since they're opening a new tab anyway, we can actually do it in Phoenix Live View, make it not only really rapid to develop, but also interactive, add that very quickly. We really had no time to learn anything. So deployed it into Amazon Elastic Container Services, which I'd already had a little bit of experience with. And my experience, actually Phoenix can actually do a lot of good really, really quickly, very rapidly in a problem like a pandemic. There was no existing middleware or API library for the contact center software, but it was really quite easy to rapidly to develop. The other major problem was the data pipeline. There were vendors who were moving data out of the public health databases, but they seemed kind of unable to write that last leg of an API layer. What they could provide was a DynamoDB subscription in AWS. And the engineers who were available to write this did not know Elixir, so they did it in Node.js and Lambda being pushed very heavily by other consultants because of the tremendous scale that we were going to be under. But both of these we did with shared values. If we can't get at protected health information, if even the engineers writing the software can't get at it, how hard is it for an attacker? And also, we were predicting in many cases processes, data, APIs, and so again, both of which could build with this sort of let it fail mentality, make it as simple as possible, and just iterate to the more correct solutions. So this gives us our first comparison, Elixir versus Node, and I caveat this with my incredible biases, but Elixir provides, an understandable runtime, concurrency based on actors, interactions with messages. For the deployment, multi-node interactions are not simple to set up in ECS, in the Elastic Container Services, but it is possible. Turns out we didn't need it. And actually building a very simple Phoenix app, I was able to run 3 tiny nodes, and it was utter overkill. If not for the redundancy purposes, we could have run on 1 tiny node. One of the concerns was actually protecting PHI, and exceptions potentially could actually propagate PHI to logs. But this application turned out to be so simple that there were no exceptions. That was actually kind of surprising to me once we actually got some error reporting hooked up. It was actually very rapidly good to write a test-driven application that actually had 0 exceptions. If there were exceptions, and I did discover that there was PHI, Elixir provides really great hooks for writing custom loggers in which to do filtering, compared to Node.js with a concurrency model built on promises. And turns out that our concurrency model was actually provided by Lambda. So, we're using libraries to actually reach out to services, HTTP, all these sorts of things, and everything gave me a promise. But I didn't need a promise for anything. I actually needed things. So, uh, so how do I just make promises go away? Lambda also doesn't guarantee that promises actually complete before the runtime is preempted. So really just don't give me promises. Just always just give me a thing. The bigger problem is this is the data pipeline. So the system is all PHI. So how do I keep that out of logs? Node.js doesn't have the at least that I know of, the sort of ability to write like nice comprehensive custom loggers. So let's take the anti-Elixir approach, the anti-Erlang, and just rescue everything, and make sure that nothing can bubble up to potentially leak data. So only cat raise and log specific variables. And unfortunately, this actually kind of conflicts with Lambda. How do I actually report error? How do I catch errors to protect information, but also bubble up errors so that Lambda actually knows that it's a problem? And the documentation implies how to do this, but not really correctly. It actually took a couple tries until we actually got this right. And one of the key problems, and I think one of the biggest differentiators with Elixir and Node.js, specifically Node.js and Lambda, was how do you know if your Lambdas are actually running, and how do you know if they're successful? A lot of these questions we just couldn't even answer. Really the only thing was log, 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 log. This gives us another comparison point. Phoenix versus Rails. The first project was in Rails, and this is where I realized, oh my gosh, I'm a functional programmer now. Everything they said was true. So again, caveat personal experiences, but Elixir's functional programming has really changed me. And in Rails, just global state, mutable state, accidental state changes were super apparent. Active record versus ecto from the library point of view. How much code in Rails were we writing to actually make active record not be active record, versus exposing like functional, very specific access to your database via change sets. There's a lot more I can go into, like metaprogramming, like yikes, hex versus Ruby gems. One of the things that was sort of a learning curve for me coming to Elixir was, like, how do I do this? Wait a minute, why isn't there a library to do this? But one of the things that I came to accept was that sometimes it's better to copy and paste like 3 lines between applications and be able to rapidly change those to meet the specific needs of the application and test those easily, than to have a library that handles every variation that you might want in those 3 lines. And don't use that one. That gem is from 2018. You don't use that one anymore. I think a big change, or a big thing for me was actually this composition versus inheritance thing. Rails does provide inheritance trees that sometimes inheritance trees with other gems that modify each other. And so hopefully they're initialized in the correct order so that the actual correct modifications to the inheritance tree bubble up in the runtime. Versus Phoenix that really provides abstractions for composing an application, where it's difficult to actually make or shared or global state. And so the cost of refactoring is actually a little bit lower. All of these allowed for very rapid development and deployment, but compared to the 3 of them, Elixir and Phoenix actually turned out the simplest, most resilient solution with the fewest errors. Again, personal bias, but so let's take a look at a little bit deeper at the data pipeline. The state database was an HL7 aggregator, and that's like saying the state database was an XML aggregator. But each lab, possibly each location or each sort of franchise of each lab, in some cases we thought creating its own integration. So imagine every possible way that data can be bad, and then multiply it by itself. There was no master patient index. So what is a master patient index? Sort of a unique ID for people in a health system that provides some like real needs. Each state runs its own MPI, or it turns out they might not. or it turns out they might actually have multiple. Um, uh, this is very USA specific, but looking in this, seeing this deep into the health system, actually some of the problems in the health system was actually kind of a shock. So here's a quick diagram of the data pipeline. And so the state database could drop a pipe delimited file every 30 minutes, but the system generating the MPIs required, extra information, extra demographic information. And so that was actually another service that the data was sent out to, held onto and sent out to this other API, but sometimes it could be hours before that could come back. So basically the data came in every 30 minutes and was held for, hours, many hours. Eventually, they'll send off to the MPI, but there are actually multiple MPIs, one perhaps for every hospital. We're sort of reverse engineering this black box, but there were not necessarily in the best public health interest. But so eventually, then they get an MPI for this person. They have to correlate it between all the other MPI systems that are built not to interop, because you actually want to run them for each hospital. You don't really want them to interop. And then eventually hand it off to us, and we can say, cool, yeah, it's in the contact tracing system in CommCare. But turns out only 7% of the demographic information was successful. So they held on to 100% of the data so that 7% could actually maybe get a better MPI. And that MPI might not actually be unique, because the same one might be generated. This is an edge case that we're not sure we saw, but there could be multiple non-unique MPIs. And then just to top it all off, they send it through a post-processing step that guarantees that any deduplication is undone. So great. I think when we first realized that, there was a lot of laughing, but also a lot of crying on our part because of the actual consequences. Contact tracing is about trust. A stranger calls you, you're sick, they're asking you to divulge every place you've been and every person you've been in contact with. This interview might be longer than an hour. And now imagine that multiple people call you on the same day from the same office to do the same interview, and none of them know about each other. So actually, duplication is actually a huge, huge problem. And every hour that a person's not been convinced to stay home might be an hour that they're actually spreading this virus. The consequence of multiple phone calls is actually lower trust in the system. And we were hearing that sometimes people would just stop answering the phone. So we're a part of the system for a while, and we helped to debug it. But fast forward to June, late one day, Randall reached out to me and said, hey, could I help him set up an encrypted S3 bucket? I said, sure. What for? A couple days later, in a secure encrypted environment, we're looking at the raw data exported from the state disease management database, which is effectively multi-table join select distinct with only the most basic filters. So every record from the beginning of time, whatever the current value is. And Randall asked, hey, could I implement a dedupe algorithm? Okay, well, let's look at some data. All right, okay, well, what are the things that we could possibly use to actually identify people? Phone numbers, no. Okay, that's bad data. Yeah. Addresses, no. Names, yeah, names could be, no, names actually are kind of bad. But maybe gender can help? Nope, that's not good. Well, there is this unique identifier called an accession number, but it turns out to be non-unique and sometimes repeated for a location every month. So no, can we be an MPI? Not, we can't be an MPI, not at all. There's no possible way that we can generate an MPI. But we actually have some fairly good user researchers at Geometer. Let's talk to some people. Talk to the people actually doing the contact tracing at these counties in the departments of health, managing the contact tracers. And yes, it turns out that data is unreliable and duplication is a huge problem. One county we learned had 2 full-time positions that all they were doing was, as data came in, was identifying the duplicates and marking it so that it would try to reduce the number of calls. But one of the key insights that we learned was that they don't care about actual manual correction. And in fact, the data is so bad that they assumed that there was going to be data deduplication efforts, and they had already hired for it. The problem, if the volume was low enough, that was totally fine. The problem was the phone calls, not the data deduplication. So coming back to this problem, can we be an MPI? Like, color me hubris, but why not? Let's give it a try. With the key insight that there was no actual MPI. If an MPI is a unique identifier that helps for deduplication, that is not an MPI. So maybe good enough is actually better. So a quick look at some data. Some names, 7 rows. If the old system, if that black box was actually doing even the smartest thing, or even though a simple thing with like names, maybe this gets reduced to 6, but probably it's 7. All 7 rows coming in as different records in the contact tracing system. But if we actually just sort of look at, okay, like middle names are problematic, turns out, but if we actually just look at first name, last name, and date of birth, we get it down to 3. We knew that we would get, from the beginning, we get it down to like 3 in here, and when we initially looked at this, we're like, that's terrible. No, we can't be an MPI, but like 3 compared to 7 is actually doing pretty good. And looking at the data, looking at the edge cases, sometimes it wouldn't be 7 records, it would be 40. And if we could get 40 down to 2, we're actually solving a tremendous problem for the contact tracers. We might introduce new problems. Might we over deduplicate records? How many John Smiths are there in a county? And also, does this algorithm bias towards English-centric naming? Possibly, but some of those edge cases we could look at and identify, we don't really trust the old system that are going to solve those problems either. At this point, we're starting to run into some problems actually doing validation, because we're doing analysis in EC2 instances because there's no way we're linking any of these files to our laptops. And CSV toolkits like CSVKit are actually really great, but they start to become kind of a pain when you have files of multiple hundreds of megabytes. But can we beat 6 hours? So the old system had been gotten down to 6 hours of holding, but can we beat that? So just a quick overview of sort of streams in Elixir. I poked around in Git for a while, and I might be wrong, but I think these might be some of the initial commits. So enum and stream we know. GenStage was something that I've been hearing about since I first started in Elixir, but always was sort of with the caveat that it's really confusing and very easy to get incorrect. Flow is actually built on top of GenStage. And it's basically to say, okay, I'm processing a stream, let me drop in Flow and let me process that stream in parallel. And Broadway, which was announced in 2019, which is a framework for building concurrent multi-stage data pipelines. And I've wanted a solution, or Broadway has been the solution that I've really wanted a problem for a while. So maybe this is it. Broadway is also built on GenStage, but I was thinking, maybe this will help me to actually build a pipeline and not have to learn GenStage. So looking at Broadway documentation, okay, that makes sense. Yeah, producers, processors, and batchers. This is wonderful. Actually, maybe I don't need to learn GenStage. So in my head, I see this diagram, and I'm like, this is great. We just start at the top left, and eventually we'll work our way around. And turns out I got it entirely wrong. That vision was something that could be built in GenStage, but you arguably might not want to. Instead, Broadway really is that producer, processor, batcher with specific callbacks. So the producer, receives messages, handle demand, gives events. If the producer doesn't produce the event in exactly the right struct that Broadway wants, you can have an optional transformer function that actually puts it in the right format. Gets through and eventually is acknowledged in some way, so it doesn't get picked up again later. So based on my fundamental misunderstanding of Broadway, I start at the top left. Let's read a file. We don't really trust the files. The contents in the files. Do rows go away and come back? I think at this point we didn't have a copy of the script that generated it, but hey, this is not too important to actually read all of this, but you have a Broadway, you start Broadway, you say, hey, here's a producer, cool, yeah, let me transform it with a function, which in our case actually says, hey, we generate a checksum for the row. We have a processor, which is a handle message, and we can delegate that out and get a response. Hey, this is a new record, or I've already seen this checksum, so just maybe update our metadata so we can know what's actually happening in the system, and eventually batch it up, send it to the database. What this actually leads to one of the problems that I created for myself in building this pipeline was this actually pipeline needs to be started up for an individual file. And so we need to actually keep some state about the file, know when it's actually finished, know when the producer's done reading, and also know when the processing's done so we can shut down the pipeline. And this is why maybe Broadway would not have been was not the best solution for this. But okay, hey, naive approach to a processor, cool. There's this stuff that I keep hearing about demand, but at this point, I'm actually staying in the Broadway documentation, and I really don't understand what demand is. But I'm like, okay, Elixir should be able to read a file really quickly. Let me just hey, loop through and push things. And Elixir, turns out, can read a file very, very quickly, so fast that the processor started giving me messages, hey, messages are being dropped. So because there's a buffer of 10,000 and it would just immediately overload it. So no, done. So getting a little bit more into the Gen stage documentation, reading about back pressure, this isn't the documentation and we don't really need to hear of it, but fundamentally, there's this thing that says, okay, it can either store the demand or return the requested event. And I still don't really understand what demand is. But hey, I can just return the requested amount, just let the demand actually let the producer work. So cool, we have a processor. Here's a file. We end up with rows in our database that we can then analyze with SQL. One unexpected thing was hey, why are all of these errors happening? The same checksums being processed in two processes at the same time. Turns out, even though it was a select distinct, there were duplicates in the file. So, okay, well, we can write a mutex around it. But turned out we actually, Broadway gives an ability to just deterministically say, you have n processes, deterministically send this message to the same process. So the same checksum can be processed serially. So, okay, does it blend? The old pipeline, they've now got down to 3 hours, but with outliers still coming in 8 or 9 hours later. The naive, most simple thing, hey, Broadway, 15 minutes, cool. 15 minutes seems really slow, actually. So looking at the CPU graphs, the CPUs are definitely not saturated. So let me just massively over commit CPUs, boom, shave off a couple minutes. But 10 minutes is actually still kind of slow to me. I feel like things can be really better. And this is when we realized, okay, yeah, every row coming in, we're doing a SQL query to actually check, have I seen this checksum before? Okay, and that's cache, boom, 25 seconds. So does it blend? It totally blends. Okay, so quickly move on through a couple more pipelines. We have test results in our database. We need to parse through them and decide, hey, what do I do with these? Who are there new people? Are there new cases? But we can build a processor that, the SQL is probably the most complicated thing, but also maybe the least relevant to this talk. But yeah, find my unprocessed test results. We have an acknowledger of the Broadway pipeline that says, hey, have I succeeded or failed? Cool, let me save an event record that says that, so the SQL can only find the test results that actually have not been processed before. So, turns out we made our own event sourcing system in SQL. Probably not a thing that I would do again, but who doesn't want to build their own homegrown event sourcing, really? And we do keep track of the last seen ID because 2 consumers can be asking for events at the same time. And while the first consumer is in process, those test results are not processed. So we need to keep track. The second one needs to, get a different batch, so we don't have the same records being processed twice. But it seems to work until it doesn't. Every once in a while, the entire pipeline grinds to a halt. So, but it's okay. I can kickstart it with a timer. Just say, hey, the handle info, handle call, handle, all these things. You can push events. So let every once in a while, if there's an idle timeout, let just wake up and push events. So okay, the next pipeline, we have data already in the contact tracing system. Let's get data out of it. There's a minimum page size of 100. Demand might be 10. So okay. Every one of these times we get a handle demand. Okay, the first one, first page for first county, put the extras on a buffer. Now, every time we get a handle demand, we can read from the buffer until we run out, make another API request, eventually run out of pages, go for the next county. And lo and behold, every once in a while, actually more often in this one, it just eventually grinds to a halt. And I add a timer, an idle timeout, but like at this point, I kind of actually need to know what's going on. So I kept coming across this documentation, except when I was looking for it. And this is where I realized, okay, Broadway is really great, but I actually need to get a little bit more into Gen Stage. This is actually in Gen Stage. So Broadway gives you, these diagrams, but the thing that is implicit, and this is actually still probably an oversimplification, is that between each stage, there's a dispatcher. So a consumer doesn't ask a producer for messages, a consumer asks a dispatcher for a message, and eventually on its own schedule, the dispatcher forwards that demand back up to the producer. And if you say demand 10 things, but the producer only gives one, the dispatcher might wait for more events to come in. It doesn't want to just flood, do too much work if more events are going to come in. So on its own schedule, the producer kind of needs to like keep track of the extra demand, basically just by incrementing an integer, potentially. And if more events come in, it says, oh, I know that there's room to handle this. Let me just push it straight down. And so in our cases, in that first case, a timer might have been the most appropriate actually solution. But in this case, looking at this, you say, okay, well, on the last page, we asked for 100, but we might get one. So, get demand. If we're only reading from the buffer, we're only going to send one, and maybe the dispatcher will actually just hang waiting for more events. So we can do the naive approach of just say, I know there's more demand. Let me just immediately make an API request. Done a second time, I might actually decouple the events from the demand. Basically say, hey, demand only reads from a buffer or increments demand. And on its own schedule, the producer is actually polling and deciding, oh, hey, I see there's more demand, but then I have events. Let me just make the API request and do something like that. Okay, so let's send the data to the contact tracing system. We can build another Broadway pipeline. However, HTTPS is really unreliable, and we actually don't trust the uptime of the system. They were actually quite good with uptime, but every system has problems. Broadway doesn't automatically give you retries, but it could be implemented. But we've already wrote our own event sourcing, so I don't know that we were at the point where we wanted to implement our own retries. And this was where Oban came in. Oban is a background job runner. Like my Ruby experience of used like delay jobs and rescue and sidekick, and this kind of like fits into that slot, does have built-in retry. With a paid license, it gives you a dashboard. And one of the key things is it does use Postgres for its queues. So, hey, pop that in. And that code actually turned out to be the most complicated thing, writing that API adapter, handling transfers and all that kind of stuff, but transfers between counties. But we have, 4 pipelines. So here comes to another comparison point of Broadway versus Oban. And I think this was one of the biggest struggles for me working on this project. I was the one who learned Broadway the best. And in some cases, as people were added to the team, I might be the only one who might actually understand Broadway. And so I kept hearing things like, I don't get this. Like I've used rescue, like Oban looks like rescue. Why don't we just use Oban? Or like back pressure, I don't understand. Like, hey, why not just like take all of these, just stick them into a queue? The Oban should be fast enough. The queues shouldn't back up. Or is there a web dashboard? Audubon gives you a web dashboard. Why doesn't Broadway give you a dashboard? And so with OBOM, the built-in retries were actually quite nice, especially around external HTTP requests. But I found that it was actually difficult to differentiate transient errors from actually systemic errors. And actually the retry mechanism rescued all errors and in some cases caught the errors so that they weren't reported to our default sort of error tracking system. And at the time, Oban Web made it kind of difficult to actually really look in and see the actual stack traces. Eventually we learned, we need to actually hook up extra error handling into Oban to make sure it gets reported at the right place. But I would say that this is actually great for async tasks and great for distributing workload across nodes, potentially without having to really learn distributed Erlang or OTP. Versus Broadway, that abstracts away just enough gen stage to get you into trouble. If gen stage actually is a good solution, Broadway is a really, really great place to start. And the docs are actually much easier to get into. It doesn't have retries or a dashboard. I have seen like a talk that showed a dashboard, but I haven't seen the code behind that yet. I haven't found that. And I would say they're both good, but maybe for different things. Like reading a file might not be the best for Broadway for the reasons that hopefully are obvious, but I also don't want to stick 400 rows into a database when only 100 of them are relevant. 400,000 rows into a database for a queue when only 100 of them are relevant. So actually, even though I might not have chosen Broadway for that, I might have chosen a tool like Flow or something like that instead. I really wish that I had known about the Open Census distributed application, like tracing framework at the time, because one of the key things in both spaces, Oban and Broadway, was actually observability. And Open Census might have given us a lot more observability into the system. I think I'm mostly out of time, so I'm gonna rush through some things. Testing. We heard, hey, there's these huge. We ran a parallel system into a different deployment of the contact tracer, and we heard, oh my gosh, only a fraction of the data is coming through. No, wait. Actually, all of those extra records are being marked as duplicates. Actually, this solves the problem. The switchover, there's a lot of coordination between the different teams. And turns out one of the benefits of actually having the multiple pipelines was that we could actually turn them on sequentially. We could turn them on conditionally. So we could actually run one, watch it reach homeostasis, do a lot of queries to see what it did, turn on the next, watch it, watch the results, turn on the next, and so on and so forth. I'd say my final thing is, like, we actually did this extremely rapidly. The data analysis in the first pipeline, I think we did in 2 weeks. The next end-to-end flow was another 2 weeks. The testing was a week, and then we went live. So I don't think we could have gone this fast without a tool like Broadway. And I think I might be out of time, unfortunately. I think unless maybe I might have another minute or two. The one thing is, yeah, go ahead.
You know what, Eric? I think we are out of time because they asked us to be pretty strict, but I'm going to try and do one thing, and I'll take one question. I've been trying to get through some of the others, but one of the ones we actually were asking about was what type of resources are actually being consistent in compute nodes and how many nodes. And I think that's really important to highlight because of how efficient it was. So could you talk a little about that?
You dropped out a little bit, the audio, but I heard sort of what, sort of nodes and that kind of thing.
Oh, sorry. How many nodes was it? Like, how many EC2 resources did we need?
We ran one 32 core instance. And actually, that was actually a choice because distributed Erlang would have actually added complexity. Also running one node with the understanding that actually, particularly because there was batches every 30 minutes, we actually had large windows in which we could do operations safely. but a single node allowed us to rely heavily on ETS without actually having to worry about distributed ETS. Yeah, I think actually a 32 core instance was actually overkill. We could have probably run just as fast on a 16 core, but it is also really fun to watch 32 cores run at 100% capacity. So that was actually pretty great.
So we're getting the kills. So sorry, Sax.
Okay.
So thank you so much for all the questions. And there are a lot of other people from the core team that actually implemented this. So
Yeah,
they'll be floating around today. So you should talk to them if you have any other questions. Thank you so much for coming, everyone.
cool. Thank you.